10 to the negative 14 again, exactly. So notice there is, if at first you're looking, 1, 2, 3, 4, 5, 6, 7, 8 different equations, but in reality we kind of only have 3, right? That one, and this one, right? Ka times Kb is also equal to 1 times 10 to the minus 14, or Kw is also used in place sometimes, all right? So know these, know how to use them. As long as you know how to do log on your calculator, you'll be fine. There's plenty of practice that I've given on the worksheets. Well, I say plenty, there's like 1 or 2, that's all you're going to need. So you can try these out, but make sure you are able to use them and identify these equations. Okay, so here we go. That's that. Okay. Next is Henderson Hasselbalch. This ends up being one of the more important parts of the exam, because you can use Henderson Hasselbalch on chapter 2 stuff like phosphoric acid, but you can also use Henderson Hasselbalch on chapter 4 stuff, which is the amino acids. So we're going to spend time on Henderson Hasselbalch. Okay, Henderson Hasselbalch. Know this equation. Again, I stress a lot to people, please bring a scientific calculator on Monday. We don't have those, and not many people carry more than one scientific calculator. Please bring one for the exam on Monday. You will need it. So the equation is pH is equal to pKa plus log of the conjugate base of whatever thing you were looking at over the weak acid. Sometimes this part is written as A minus over HA, whatever form you prefer to memorize it as, go ahead, but it means the same thing, conjugate base over weak acid. So, again, make sure it's still recording. So, how do we use it? When do we use it? The very first thing you need to check, if you're allowed to use Henderson Hasselbalch, is if your reaction contains a weak acid and a conjugate base. They can be in the reactants, they can be in the products, whatever. It must include a weak acid and its conjugate base in order for you to use Henderson Hasselbalch. It gets even slightly more complicated than this, and that if your reaction also contains a strong acid or a strong base, you have to do some stoichiometry first before you do Henderson Hasselbalch, which we will do an example of right now. So, I'm lazy and I don't make new questions, so I'm going to go back to this. And let's do this one right here. We'll do the hard one. We'll do that one. So let me write down the information on this piece of paper real quick, and then we'll work on it. This again is on the chapter 1 and 2 SI worksheet. We have H3PO4, 1 molar, 100 mils, and we have NaOH, 1 molar, 250 mils, and we are told H3PO4 has a bunch of pKa's, 2.15, 7.2, and 12.4, and they want the pH of this reaction. Again, for those listening at home on the recording, this question is on the chapter 1 and 2 worksheets. So let me flip back to the document. All right. Okay. I hope this works out. I'll record every SI session if this ends up working. Okay, so what we have here is a weak acid, phosphoric acid, and NaOH, which is a strong base. Oh yeah, for how do you know if something is a weak acid or not? The way I memorize it is that there are only 6 strong acids, so any other acid is what you call a weak acid. So let me write that list real quick. Strong acids from Gen Chem. Any more? There's one chair somewhere? It sounds like there's one spot somewhere. Another one over there too. All right. Okay. Oh, that's good. That's like the lottery there. All right. Wherever you like. 50 students bringing their own folding chairs in here. I gotta stop it when it becomes that. Okay. So, your strong acids. These are your 6 strong acids: HCl, HBr, HI, sulfuric acid, nitric acid, perchloric acid. Any other acid is going to be considered a weak acid in this class. So H3PO4 therefore is a weak acid. All right. NaOH, CaOH, anything with like a ionic type molecule with the OH. Raise your hand if you haven't signed in yet. All right, a couple around here. Okay. So yeah, NaOH, CaOH, any ionic compound with an OH attached to it is a strong base. So let's do the actual reaction. Let's write it out. This is stoichiometry stuff in, I can't remember, Gen Chem 1 or Gen Chem 2. So when we have an acid reacting with its base, what's going to happen? Well, this base is going to steal a hydrogen from this, and you make H2PO4 plus sodium and OH ions, not OH ions, excuse me, plus sodium and water, neither of which matter in the Henderson Hasselbalch equation, so I'm just going to cross them out. It does not matter. The only parts that matter with Henderson Hasselbalch are your weak acid and your conjugate base. All right? So, and again, the way acid-base reaction works is that the base is going to steal hydrogen from H3PO4 to produce H2PO4. Okay. Let's fill in the information. So, 1 molar, it's a little cut off here, 1 molar at 100 mils of this, and 1 molar of 250 mils of this. We can't do stoichiometry with concentrations. If you haven't signed in yet, you can sign in at the end. We can't do stoichiometry with concentrations. We have to convert everything into moles. And in fact, sometimes on the exam they may just give you the moles. But if you're in this situation where they give you concentration and volume, you need to convert it into moles. So, how do we do that? Well, remember that molarity is equal to moles per liters. So 100 milliliters is 0.1 liters. You do the math here, you find out you have here 0.1 moles of H3PO4. You do the same thing over here, you find out you have 0.25 moles of NaOH. Just do 1 molar equals X moles over 0.25 liters. You end up with 0.25 moles there. Now you're allowed to do stoichiometry. So what stoichiometry is to figure out how much product is made and how much of any reactants are left over, if any. So the way to do that is you pick out the limiting reactant, which is simply, for this class especially, is just whichever you have the least thing of, which is, in this case, H3PO4 is our limiting reactant. We have less of it. So we do some math where reactants are being used up. So because this is the limiting reactant, it's going to go to 0. What happens over here? We end up with 0.15 moles of NaOH. And how much product do we make? We started with 0 product, 0 moles of H2PO4, and we're producing 0.1 moles of this thing. We end up with 0.1 moles of H2PO4, okay? All right, so yes, question?
Okay, so when it's in the reaction, it's supposed to subtract.
Yes, yes, anything on the reactant side is subtracted, anything on the product side you must add.
You add, okay, and then you have a 0 mole because
There wasn't, we didn't start with any H2PO4, exactly. Yeah, for this, I know in Gen Chem you sometimes start with product or whatever, you don't have to worry about that here. This is more straightforward stoichiometry here. Let me check this, is still recording, okay, good. All right, so, before you do Henderson Hasselbalch, you have to see if it's okay to do that. We, unfortunately, can't do Henderson Hasselbalch yet because after doing stoichiometry, we still have NaOH left over. Again, you're not allowed to do Henderson Hasselbalch if there is any NaOH left over. So, are you stuck? No, because phosphoric acid is a polyprotic acid, it has more hydrogens to give up. To continue this question, I'm going to have to flip over the page. We're going to react our H2PO4 with our remaining NaOH. So I'm going to flip the page. Nope, I'm going to do a new page. Okay. H2PO4 plus NaOH gives you H1PO4 plus stuff that doesn't matter. Okay. Based off our last page, we had 0.15 moles of this. Notice we don't have to calculate moles anymore. We have to convert concentration to moles anymore. We can just carry the moles over from the previous part. And we produced 0.1 moles of H2PO4. Same thing, stoichiometry. This is unfortunately, again, the limiting reactant. So we do that. This is 0. This becomes 0.05. We're almost there. This one over here, we started with 0. We didn't have any H1PO4. We now produce 0.1 moles of this thing. We still can't do Henderson Hasselbalch. There's unfortunately still some NaOH left over. Is there any more hydrogens to give up? There is one more hydrogen to give up from phosphoric acid, so we are going to continue on. H1PO4 plus NaOH gives you just PO4 plus stuff that doesn't matter. Let's see if we finally get rid of the NaOH. We carry over the 0.1 moles of H1PO4 that we made in the previous reaction. We carry over the 0.05 moles of the NaOH that was left over from the previous reaction. Finally, the limiting reactant is NaOH now, because there's only 0.05 moles of it. I'm going to subtract 0.05 from both of these. This becomes 0. This becomes 0.05 moles. And finally, our product, we started without any PO4. We're going to add 0.05 moles to it, and we have produced 0.05 moles of PO4. Now we check to see if we can do Henderson Hasselbalch. We don't have any strong base anymore. We just have our weak acid and its conjugate base, so we are now allowed to do Henderson Hasselbalch. So I'll write out the equation, then we have to put in the numbers in their correct spots. So the beginning of this question, by the way, which feels like a century ago, is figure out the pH of this reaction. So we're going to find out pH by filling in the rest of this equation. So 1 second. Conjugate base over weak acid. Okay. Well, we're kind of lucky that the conjugate base and the weak acid happen to be the exact same number. It won't always be like that. So how are you supposed to know which is the conjugate base or which is the weak acid? Especially, it might not be that easy to tell when you look at amino acids. The answer is the following. The one with more hydrogens, no matter what it is, the one with more hydrogens you are going to pretend is the weak acid. The one with less hydrogens you're going to pretend is the conjugate base. You can even simplify it even more than that for amino acids. The one that is more positively charged is your more acidic thing, and the one that is more negatively charged you're going to consider is your conjugate base, okay, for these types of reactions. And we'll go over an example of that in a second, all right? So don't worry about it. We'll go over an amino acid example in a little bit. Okay, so both of these are going to be 0.05, so I'm not going to bother writing that in. Just plug in 0.05 in your numerator and your denominator here, and you do the log of 0.05 divided by 0.05. You'll be astonished to see that becomes 0. So we are left with the pH of this reaction is equal to pKa. We have 3 pKa's to choose from, right? Let me go back to the question real quick. We have 3 pKa's to choose from. How are we supposed to figure out which one we're supposed to use? You do so by remembering that the lowest pKa represents the first hydrogen that was given up. The second pKa represents the second hydrogen was given up. And the third pKa represents the last hydrogen that was given up. So, since we had to go all the way to the last hydrogen that was given up, we say, therefore, the correct pKa to use here is 12.4. You would be given the 3 pKa's on the exam. It's just up to you to choose which is the correct one to use. So the answer to this question ends up being 12.4. Okay? Any questions on this? I know it was long, but luckily it's recorded. Yes?
Sorry, I know you just said this. Can you go over again why is it 12?
Why is it 12.4, right? So the bottom line is we have 3 different pKa's to choose from. Each one, no matter amino acid or this stuff, represents a hydrogen that is going to be donated. So we had to do 3 reactions in order to finally get to the point where we do Henderson Hasselbalch, so we had to use the last pKa.
If it was H3, it would be 2.5.
Yeah, if we were good, if we somehow we did this first reaction and we didn't have any NaOH left over, we would use the first pKa, because we would only need to donate 1 hydrogen. And I believe there's an example of that on the worksheet also.
Right, and then H2 would be seven.
It would be the second one, yeah.